In this video, I'd like to talk about some properties of the definite integral and then use those properties to calculate some integrals. And also I'd like to point out one warning. Okay, so sometimes the limits of integration are interchanged. For example, suppose that we have on the number line, all right, we have A is here and B is here. Up till now, the bigger number was the upper limit of integration. The smaller number was the smaller limit of integration. But let's take a look at this in light of the fundamental theorem of calculus. Suppose that capital F is an antiderivative of little f on that interval. And if I evaluate this backwards, starting at the bigger value from A to B, all right, up the definite integral from from b to a, the definite integral of little f of x dx, that would be capital F evaluated at the upper limit, a, minus capital F evaluated at the lower limit, b. But remember, b is the bigger number. This would be the opposite of capital F evaluated at b minus capital F evaluated at a, or the opposite of the definite integral as we've known it, the integral from a to b, from the smaller value to the bigger value of little f of x. So we have this first property. If we interchange the limits of integration, we just change the sign on the definite integral. If we interchange the limits of integration, we change the sign on the definite integral. Okay? Another property, suppose that f is defined at a, all right, and big F is an antiderivative on some open interval containing a, then the definite integral from a to a of little f of x dx would be capital F of a minus, and this should have been gone, capital F of a. Capital F of a minus capital F of a is 0. So if we integrate from a to a, starting the lower and upper limits are the same, assuming that the function is defined there. All right, if we calculate that definite integral turns out to be 0. Okay? All right, one more example. All right, suppose that f is continuous on an interval containing a, b, and c. All right, and this is, and suppose that capital F is an antiderivative of little f on this interval. We don't really even need that. But then the definite integral from a to b plus the definite integral from b to c of f of x dx is equal to the definite integral from a to c. And think about the picture of this. This would be the definite integral from a to b of f of x dx would be this area. This would be the definite integral from b to c of f of x dx. And the whole thing would be the definite integral, all of that area would be the definite integral from a to c of f of x dx. All right, so this, I mean, geometrically, this area plus this area is this area. Okay, as it turns out, this works, you know, in this case I've drawn this so that a is less than b is less than c, but if a, b, and c can be arranged in any order of, you know, and that property would still work. Okay. Now, let's take a look at the fundamental theorem of calculus. All right, the fundamental theorem of calculus has this statement. The theorem says that if f is continuous on the closed interval from a to b, and f of x is any antiderivative of little f on a to b, then the definite integral from a to b of little f of x dx is capital F, the antiderivative evaluated at the upper limit, minus the antiderivative evaluated at the lower limit. Let's take a look at this with this example. Let's suppose that we use this here, all right? And if we use that, well, this is going to be the definite integral from -2 to 2 of x to the -2nd. And that's going to be, all right, well, when I antidifferentiate x to the -2nd, I'll get x to the -2 plus 1, that's -1, over -1, evaluated from -2 to 2. All right, let me rewrite that. That would be -1 over x evaluated from -2 to 2, and that's going to be -1/2, 1 over x, minus a -1 over -2. Okay. And this is going to be a -1/2. All right, minus, well, this would be a +1/2. So 1/2 minus 1/2 is -1. All right, now let's take a look at that. That looks perfectly reasonable. Let's take a look at this. All right. All right, now here is the graph of the function 1 over x squared starting at -2 to 2. Notice the discontinuity right in the middle of that interval, right at 0. We integrated from -2 to 2. Notice the discontinuity right at 0. All right, first of all, we got a negative result, meaning there should be some area below the x-axis. All right, there is no area below the x-axis. This is all above the x-axis. All right, second is the value. If I look at this, all right, we got -1. Here is a square, all right, with area of -1. Clearly, there's more area here than in that square. All right, so what went wrong? Well, what went wrong, of course, was this discontinuity in the middle of that interval. Remember, the definite integral, the fundamental theorem of calculus, works is provided that the function is continuous on the integral that on which we're calculating it. So we have to be calculating it over a continuous function. So again, the answer, all right, continuity, this function, we got the wrong result, all right, because 1 over x squared is not continuous on the integral of integration, which was -2 to 2. So that was a problem for us. That was a problem. Okay, let's take a look at another example here. All right, let's suppose that I want to integrate f of x, which is f of x is defined piecewise, and it's 1 minus x. It's 1 minus x if x is less than or equal to 0. So here's the 1 minus x when x is less than or equal to 0, when we're on or to the left of the y-axis. And it's x squared plus 1. All right, we have this parabola. If x is, excuse me, is greater than 0. And so now what we'd like to do is we'd like to calculate the definite integral of this function. This function is continuous, so we shouldn't have a problem. The definite integral of this function on the interval from -1 to 1. Well, of course, right in the middle of that integral is where this thing splits, okay? So let's see, how would we do that? I'm going to do this off to the side here. I'll start it anyway. The definite integral from -1 to 1 of f of x times dx is equal to, now remember we had that property, the integral from a to b plus the integral from b to c is the integral from a to c. Well, we have a to c, and we can split that up, a to b and b to c. And so this would be, and where I'm splitting it is I'm splitting it at 0 because that's where this function changes rules. So we'll integrate f of x from -1 to 0, because f of x follows one rule from -1 to 0, and then the integral from 0 to 1. Why? Because f of x follows a different rule from 0 to 1, when we're bigger than 0. And of course, this is the integral from -1 to 0 of 1 minus x, plus this is the integral, all right, from 0 to 1 of x squared plus 1. Because the rule on this interval, all right, from -1 to 0, we follow the rule 1 minus x, all right, for this function. For this function, from 0 to 1, we follow the rule x squared plus 1. x squared plus 1. So now let's calculate each of these. Each of these I can calculate using the fundamental theorem of calculus. So an antiderivative of 1 is x, the derivative of x is 1, minus antiderivative of x is x squared over 2, and that goes from negative 1 to 0. Plus antiderivative of x to the x squared is x to the third over 3, plus antiderivative of 1 is x, and that goes from 0 to 1. So let's see, so let's evaluate this at 0. I'll have 0, all right, minus 0 squared over 2, okay? And I'm just going to put this first integral in square brackets, minus, evaluate this at negative 1, I'll have negative 1, okay, minus negative 1 squared over 2, okay, that'll be the value of this first integral, and then plus, all right, for the second one, I'll have 1 to the third over 3, 1/3, plus 1, oops, let me use B, minus, the value at 0 is 0 to the third over 3 plus 0, and that would be the value of the second one. So let's see, so what do I have? I have negative 1 minus 1/2 is negative 3/2. Well, so I have 0 minus a negative 3/2 from this first one, plus I'll have 1/3 and 1 is 4/3, minus 0 from the second one. So I'll have 3/2 plus 4/3. Excuse me, we can get a common denominator of 6. So this would be 9/6 plus 8/6. All right, and together that would be 17/6. So that's 17/6. So notice that this is the area here is 3/2. The area here is 4/3. We'd expect it to be a little bit smaller because if you look at, we have this sort of trapezoid here, but here instead of having the trapezoid, it dips down. So we've lost a little area, and so altogether the area is 17/6. 17/6. Okay, almost three square units. Okay, let's take a look at one more. And this is a lot the same. This is the idea of integrating an absolute value. The absolute value, the integral from definite integral from 0 to 4 of the absolute value of x minus 2. And notice what happens here. If I look at this, all right, here's the function x minus 2, all right, from 0 to 4. All right, but I don't have that function. I have the absolute value of this function. Now, wherever this function is negative, when I take the absolute value, all right, it makes the negative parts positive. So the absolute value looks like this. The absolute value looks like this. So, and notice where that was going to change is where this expression is 0. 2 makes x minus 2 0. So let's take a look at how this would work, how we calculate this. This integral from 0 to 4 of x minus 2 in absolute values times dx is equal to the integral from 0 to 2 of the absolute value of x minus 2 dx plus the integral from 2 to 4 of the absolute value of x minus 2 dx. Now remember, and how did I pick this 2? All right, how did I get this 2? Well, the 2, if I set the x minus 2, the contents of this, to 0, x was equal to 2. Now notice, if x is between 0 and 2, say at 1, this is negative, so the absolute value is going to change its signs. So this is going to be the integral from 0 to 2 of negative 1 times x minus 2, because that's what the absolute value will do. It'll change the signs. Plus out here, say x is equal to 3 on this interval, all right, we'd have this as positive, so the absolute value is not going to do anything to it. It's going to leave it alone. Okay, let me rewrite this once more. So this here, 0 to 2, would be positive 2 minus x dx, plus this one, integral from 2 to 4, we don't have to do anything because the absolute value doesn't do anything. Now notice we have integrals without the absolute value that we can calculate using the fundamental theorem of calculus. So first of all, antiderivative, 2x minus x squared over 2 from 0 to 2 plus x squared over 2 minus 2x from 2 to 4. All right, evaluating this at 2, I'll get 2 times 2, x is 2, 2 times 2 is 4, minus 2 squared is 4, divided by 2 is 2. All right, and then when I evaluate it at 0, I'm going to get just 0. 2 times 0 is 0, 0 squared over 2 is 0. Okay, so that will be the value of this first integral, plus when I evaluate this at 4, I'll get 4 squared, 16 divided by 2 is 8. All right, minus 2 times 4 is 8. Okay, that's going to be 0. All right, then minus the value at 2. 2 squared is 4, divided by 2 is 2. And I'd be subtracting 2 times 2, 4. So this is going to be, then, 4 minus 2 is 2. Minus 0 is 2, plus I'll have 0 minus a negative 2, so 2 plus 2 is 4. Okay, so the value of this integral is 4. Notice how we had to basically break this up as to where this function would be positive or negative. The contents of the absolute value would be positive or negative. If I look at this again, notice if I look at this, these two, we have two congruent triangles. Each of them has a base of 2 and a height of 2. So using the formula, I get 2 units of area here, 2 units of area here, 4 units of area altogether. All right, so there were some properties and how we can use them to calculate definite integrals.